All right, we're going to go ahead and get started here. I want to thank EasyPower for putting on this webinar. My name is Dave Komm. I'm a solutions engineer with Mersen. And for those of you on the call that aren't familiar with Mersen, we were formerly Ferrule Shamit, and about 7 years ago we changed our name, Ferrule Shamit or Gould Shamit, whichever of those names you remember. So our primary focus is fuses and overcurrent, over voltage protection. So we're going to go through kind of some basics on fuses today. So getting into the presentation, we're going to talk about typical construction methods, some of the components we use in our fuses or in fuses in general, types of operations, whether short circuit, overload, cycle fatigue, go a little bit into UL fuse classes and different types and why we have each type. And if you guys have any questions, there's a questions box, just type them in there and I'll try to answer questions at the end. So looking at our first type of fuse construction, it's going to be a Ferrule design, typically up to 60 amps in the UL style fuses. And this is a traditional, when you hear dual element time delay fuse, this is that type of construction. So we call it a spring and plunger assembly. So we start with this little housing to house a spring and a plunger, which is shown here. And then we add a heater tab, and really all this is doing is helps to focus some heat, and it does carry the current. It is the electrical connection within the fuse. Then we add a short circuit element, and we'll talk about how these parts interact with each other a little further on. Typically, short circuit elements are going to be copper or silver, depending on the fuse, depending on cost, things like that. Performance would determine what types of metal we use in there. And you can see this element has kind of a U shape to it. That's just for manufacturability, that if we had it with a flat element, it'd be a lot more flimsy. So adding those U-bends to them is really just adding a little more rigidity to it. So when we're assembling it in our factories, it's easier for people to handle and work with. Then we add this little rubber grommet, and really all that's doing is helping keep any of the filler material from binding up and getting stuck in that plunger assembly when that tries to operate. So really just making sure there's no sand getting wedged in there. Then typically we'd slide a body on the fuse, put one end cap on, and once we've done this, then we will fill it with sand. Typically we're using a silica sand. We know right down to the grain size of the sand we're using in there, and different mixtures to get different performance out of them. And we'll fill the fuse, and then we'll actually put it on a vibration table to try to compact that sand down as much as possible. We really want it to be a good compact fill in there. So we'll do that step a few times, maybe 2 or 3 times of filling it, vibrating it, topping it off again, vibrating it, and really making sure there's a good compaction of fill in there, fill media. Then we put the other end cap on, and typically on these it's a blind solder where it's brazed after the end cap is put on, and then everything's heated up and brazed together to make a good solid electrical connection in the fuse. So it's typically up to 60 amps, could be 100 amps. 100 amps is kind of could be a mixture of this and the next design we're going to see, depending on the fuse types that's being used. So when we get over 100 amps, typically a lot of manufacturers start to do a blade block assembly. And when we look at these, it starts with a block, and then we braze a blade to it. And you can see in this drawing, it looks like 2 different materials. Typically they are. The block would be like a brass material, and then the blade being copper. And really just to get costs down, if we made that whole thing out of solid copper, it's going to have a higher cost on the fuse. And really the performance benefit of doing that versus brass doesn't outweigh the cost benefit. So traditionally it's 2 different types of material, and then we do plate them usually. Some fuses do use aluminum, like a solid forged aluminum end cap. Then from here, we start to add elements into the fuse. So this fuse typically is going to have more than one element in it. Again, elements would be typically copper or silver. We do use some other types of materials if they're real low current rated fuses. You could get into some different materials there, but typically copper, aluminum, or copper or silver, excuse me, are going to be the most common materials. And you can see in here there's these little notches, little circles. So those are stamped out, smaller cross-sectional areas, and that's what's going to open on an overcurrent short circuit type condition. Each set of those notches is roughly about 125, 150 volts, somewhere in that range, depending on design. So when we're talking fuses, typically when you see a medium voltage fuse, 15 kV, it's going to be a lot longer than a 600 volt fuse, and that's because we have more of those notches in there. And typically those elements, I don't show them in this, but they're typically wound around a core. Or 600 volts, we can do it in a straight line. And then on this fuse, because it is a higher current rating, we're going to stack elements. So if we said this was a 400 amp fuse, we're going to have 4 essentially 100 amp elements. And again, that's kind of a performance thing. It's easier, or we can melt 4 smaller elements quicker than we could if we had one element that was 400 amps versus 4 100 amp elements. And when you get up into 1,000 amp rated fuses, couple thousand amp rated fuses, there's probably 100 different elements in there, and it's really to get the speed out of the fuse, get it to be very current limiting, rather than trying to melt one big solid element. We split it out across many smaller elements. And then from here, so what we would do is solder on the other blade block assembly and put a body on it. Again, we would add filler at this point, typically a silica sand, through one of the holes you can see there in the end of the block. Again, vibrate it down, really make sure there's a good compaction of fill material inside. And then once that's done, the fuse all gets plugged up. So I want to try doing a poll question. I've never tried these before. So I just opened a poll question. So I want to get everyone's opinion. What's a harder voltage for a fuse to clear, direct current or alternating current? And this is kind of going along the lines of, like I was saying, each element or each notch section, it's 125, 150 volts. So it looks like a lot of people have answered, about 75%. So we're at 41% saying alternating current, 59% saying direct current. So direct current is harder for a fuse to open. I always like to ask that question because it's always split almost 50-50 on what people think. Generally, when you don't see, when you see a voltage rating on a fuse and it doesn't say AC or DC, it's assumed that it's AC current. DC is much harder for a fuse to clear because it's a steady state voltage versus an alternating where it's at some point going to be driving itself back down to zero. Direct current, the fuse has to drive everything back down to zero. And with that, voltages are a maximum rating. So got another poll question. What happens when we use a fuse over its maximum voltage rating? So I just opened up a poll. So nothing happens, the fuse acts like it should, opens safely as soon as power is turned on, opens catastrophically when power is turned on, or nothing until a fault occurs and then it opens catastrophically. Okay, so we're at about 70% response, 75% response. So the winner is nothing happens until a fault occurs, then the fuse opens catastrophically. 60% of people responded to that. That is the correct answer. So if you install a fuse, a 600 volt fuse on a 1,000 volt system, you go and you turn the switch on, nothing's going to happen as long as there's no overcurrent present. once the fuse tries to open and it sees that excess voltage, what happens is it kind of runs out of notches here. So we only have so many of those notches to spread the voltage out across. And by the time it hits that voltage, it's got nothing else to do, and it starts burning away portions of the element where it's not designed to. And it could lead to a catastrophic failure. And we have a high power test lab, so we get to kind of test different things within our facility. So I always like to show some videos. This was actually a DC test. It's a 600 volt DC fuse that we were trying to see if we could push 1,000 volts through it, just to try to see what the fuse would do. Maybe it could handle it, maybe we over designed it. And as you can see, the fuse really did not like trying to clear on 1,000 volts where it was only 600 volt rated. And we kind of let it sit here and burn for a little bit. And if I had the sound on, you'd actually be able to hear our lab manager in a few seconds here say, I think that's enough. What happens is the fuse is essentially completely out there, and now it's arcing across our rectifier terminals, is what wound up happening there. All right, I can show this one again. So it's a good video, and I do have a couple more videos I'll show during the presentation from our lab. So moving on, talking about fuse performance, overcurrents, just to make sure everyone's on the same page here. We're talking overcurrents, anything that's in excess of a continuous current rating. Two types of overcurrents, short circuit or fault, can be used interchangeably, those terms, and then an overload. So what are we talking about here? Again, I would assume most of the people on the call are familiar with these terms. I just kind of like to set a baseline. So anything that's an excess, insulation breakdown, falling metal objects, those are types of things when we're talking short circuit or faults, accidental, phase to phase, fault conditions, high current, hopefully short time period. And then what are we trying to prevent, whether it's using a fuse, a circuit breaker, whatever the device is. So this is another lab test we did. This one is in slow motion. This is about a 750 MCM cable that we loop between the bus bars, and we're going to apply a short circuit to it. Again, slow motion, I know it's not the best quality video, but you can see those electromagnetic forces begin to whip around the cable. There's a tremendous amount of heat there. We left the insulation on. That's what all the smoke is. Insulation burning off, and those forces. So that's what we're trying to prevent when we're talking short circuit fault conditions. Overloads, just the opposite of that. Anything that's going to be a lower current and will cause damage over time if allowed to persist. Typically fires, that would be the biggest cause or biggest effect of it. Again, we have, I'm going to play this. This is a real-time video now. 750 MCM cable between two bus bars in our lab. We did strip the insulation off for this test. And then we're just going to sit here and overload the cable. And we'll see right about now, it's going to start sagging under its own weight as that heat starts to build up in the cable. And we let this go to the point of failure, really, to show if there's nothing there to take out an overload, they can be pretty hazardous. At this point, it's like a large light bulb, bright red, and then eventually the cable is going to get to the point it no longer can hold it, melts completely off. This incident in our lab actually did cause a fire. We had a little rubber mat. You can see all the black smoke that the cable landed on. See the flames kind of hitting the bottom of the screen, and then the fire extinguisher. So this overload, we actually did cause a fire. So fuse performance. Within EasyPower, you guys can pull up all these characteristics, all the curves, time current curves. So typically, the lower portion is going to be the short circuit region, the 0.1 and lower, and then above is going to be considered more overload, the overload portion of the curve. How do we read them? Fairly easy. So we find the available current on the horizontal axis. So in this case, 400 amps RMS available, and then the fuse will take 30 seconds to open 400 amps in this particular example. Another data performance kind of hand-in-hand operation is peak let-through current. So on the horizontal axis, we have available current in RMS, peak current going up the vertical axis. So to read these again, we would have our available fault current on the bottom. In this case, 20, 30, 40, 50,000 amps available. We follow it up till we hit the fuse curve, go over, and you can read the peak let-through, which is 9,000 amps. Now we got to remember, in this case, we're not comparing apples to apples. It's RMS current to peak current. And I'm sure some of the people on the call have heard the up, over, down method if you want to get RMS let through. So you can take that 50,000 amps, hit it, follow it up till you hit the fuse curve, over till you hit this grayer line, and then back down. And what that gray line is the actual maximum amount of current the test circuit could produce if the fuse wasn't there. So when we look at this curve, we can also determine the current limiting point of the fuse, where it splits off from that gray line. That is where the fuse is going to start entering its current limiting range. Before that, it's going to be thinking it's more of an overload, and it's not going to be current limiting. It'll take a longer duration to open. So when we look at a fault here, we have full load current in green, our available fault current in red. The fuse is going to open, typically if it's a short circuit, a current limiting fuse is going to open in that first quarter cycle and limit the amount of peak current that's there. We zoom in on that. Peak current, how we're getting that measurement, it is just the peak value of that let-through curve. And then when we're talking performance on short circuit, how a fuse operates. So the first part of this, the rise time, is going to be a melting I squared T. It's a measure of thermal energy. And what's happening at this point, the fuse is melting in all these notches up on the top, the 4 notches that we have in the short circuit portion. They're going to be continuously heating and heating and heating. When it hits that peak, what happens, there's an arc that forms because the element has melted at those portions and the voltage is arcing across them. And then the second half of this let-through curve is the arcing time, or arcing I squared T. The total is a clearing I squared T. So as that's arcing, all that sand filler that we compacted in there fills in around the arc and quenches it. And what the sand actually melts and kind of turns into a glass-like material, which is a great insulator and helps disconnect the circuit. And why are these values important? If we're talking about selectivity or coordination between 2 fuses, we have to look at the time current curves, but we also have to consider the portion that's not represented on the time current curve, which is below 0.01 seconds. And we have to look at the branch fuse, what the clearing I squared T is of that fuse versus the melting I squared T of an upstream fuse. So in this example, the downstream fuse has a clearing I squared T of 1,000 amps squared seconds. The main fuse has 1,500 amps squared seconds. That downstream fuse will fully clear before we melt the element in the upstream fuse. And that's a portion, so there is another side we have to look at when we're trying to coordinate fuses not just looking at time current curves. So overload portion, I'm going to show the time delay dual element. So what happens on the spring plunger assembly, where the connection is, there's a eutectic solder here, and that solder is designed and calibrated to melt at a specified temperature. And once that heats up and hits that temperature, it melts, and this whole spring draws that plunger back and disconnects the circuit. You can see up in the top picture of the fuse cutaway. And that's how we're doing typical on a dual element time delay fuse, how overload protection is achieved. So we're talking fuse operation, standard motor characteristic, starting motor characteristic. Just going to represent that with lines across the top on a time current curve. So the importance of a time delay fuse is that we can size it closer to what the full load current is and achieve motor starts is really where it is. So in this example, we have the blue fuse that is a fast acting or a non-time delay fuse versus a time delay fuse in red. And you can see where the curves line up versus a motor starting characteristic. That the 100 amp time delay, we get a little more room in the middle of the curve and we're allowed to start the motor. So this brings me to my last poll question I made. So out of these two fuses, which fuse is more current limiting? The non-time delay, which is the A4J represented here, or the time delay fuse, the AJT? About 3/4 of the people voted. So the results from what everyone voted on, 51% fast acting fuse is going to be more current limiting, 16% the time delay is more current limiting, and then 33% said they're equal. Not uncommon results when we ask the question. From this curve, we can't tell which one's more current limiting. We have to look at a peak let-through curve, and I do pick the 100 amp fuses in this example for a particular reason. When we look at this, here's our time delay fuse. So peak let-through, if we remember that point where we split off, that's where the current limitation starts on this fuse. Now I draw our fast acting fuse over it, and we can see now that the time delay fuse is going to be more current limiting. And I generally ask the question because people think fast acting, they think that means more current limitation, and it does not necessarily mean that. It just means it doesn't have a time delay built into it. In many cases, time delay fuses are a newer design, and they're going to be the better design of the two and have more current limitation built into them just because they're newer designs and newer technology, things like that. So you can always use a time delay fuse even when you don't need the time delay, unless we're talking semiconductor application, which is a whole different world, but in the general scheme of wire protection, things like that, you could always use a time delay fuse, and generally speaking, they'll be more current limiting. Now, when we talk cycle fatigue, particularly with motors, obviously that can be a big thing with motors starting, stopping, pumping things. What happens in a fuse is, when you think about it, the fuse is heating up and then it cools down, and then it heats up and then it cools down, heats up, cools down. You keep going through those cycles. And if you cut a fuse open that has opened and you suspect cycle fatigue, you actually look at where these notches are, and we get little S bends. And what that is the heating, the expanding and contracting of the metal kind of form little S. You can see the bends there in the smaller areas when you dissect the fuse. And over time, that can only expand and contract so many times. And then typically you get one set of them that just breaks. So it's like folding a piece of copper back and forth a bunch of times. At some point it's going to break. And that's generally what happens on cycle fatigues. And you can tell that just by dissecting it, looking at these areas. Sometimes you can see it by the naked eye. A lot of times you need to use a microscope to look to be able to see those bends. It kind of depends on what the current is there that we're cycling through, how drastic it is and how much it's expanding that metal and contracting it. but there is a lot you can tell by doing that. Now, general overview of UL. UL 248 is the fuse standard for all UL low voltage fuses. So these are the primary classes. Class L fuses go from 100 amps all the way up to 6,000 amps, 600 volts only. Class J's are going to be 600 volts, 0 amps to 600 amps. Class T, we offer them in either 600 volts or 300 volts, and those can go up to, the 300 volt is up to like 1200 amps, 600 volt is up to 800 amps in these classes. Generally real small, compact size, no time delay in the Class T's just because the body's so small we can't really get the performance we need for a time delay. And then we have Class K5, which is an older one-time, if you hear someone say one-time fuse, that's generally what they're talking about. Not the greatest fuse, but it's there. 600 volts, 250 volts, 0 to 600 amps. Then we jump to an RK5, which would be, again, 600 volts, 250 volts, 0 to 600 amps. RK1, same thing, it's 250 volts, 600 volts, and we can go up to 600 amps. CCs, that's a control circuit fuse, 30 amps and lower, 600 volts is what those are offered in. And then midget fuses, again, typically 30 amps and lower, 600 volts, but they could be 250 volts. There's no real UL definition. It's whatever the manufacturer picks for the fuse. And those are supplemental protection only. Different body breaks for anything below 600 volts. So 60 amps and below, like I said earlier, it's going to be that Ferrule construction, Ferrule design. And then when we get above 60 amps, we start getting into bladed product for UL. So just want to show those body size breaks for the fuses. Then when we talk, when I had K5, RK5, and RK1 on the slide a few slides ago, they're all very similar. And it's really like a history lesson here. In this one, I added Class H, which hopefully no one out there sees or uses. They're the old renewable screw-on end caps. Not great fuses. There's no fill in them. Like I said, the fill helps quench arcing, so it actually helps drive current limitation in a fuse. So we go from H, which is non-current limiting, only 10,000 amp interrupting rating. So fairly low by today's standards for as far as what it can handle for current. Then K5, we get into a fill, but it's not a silica fill typically. They're going to be a lower cost fuse. Those are going to be 50,000 amp rated. And then into an RK5, which we start getting into silica sand. Typically it's going to use a copper element, 200,000 amp rated. And then an RK1 is going to use a silver element, and again, 200,000 amp rated. It's kind of a history lesson of how we've progressed from Class H being the original design of a fuse going way back 100 years, and then getting to RK1, which would be the newest progression, latest and greatest design of them. And what that means when we're looking at let-through curves here. So Class H and K5, K5 would be on here. It's not considered current limiting by UL, so it won't limit to the first quarter cycle. Class H is not current limiting and won't really limit even close to quarter cycle either. When we look at RK5 and RK1, you can see there's a drastic difference here. It's an 80% reduction in let-through energy when we go from an RK5 to an RK1. So very drastic there. And then Class J is going to be closer to RK1, but a little better. Typically speaking, Class J fuses are used for new installations. RK1 would be used for retrofits in a plant. We have existing safety switches, things like that. you'd throw an RK1 or an RK5 in there. And then from an arc flash standpoint, I like to show this video. So first test, no fuses and an arc flash. This is going to model a molded case breaker. This is real time, 18,000 amps, real time test. So we can see the arc flash with 6 cycle breakers, what's actually disconnecting the circuit here. Now we're going to install RK5 fuses. And that's all we did was remove the breaker, install RK5 fuses. So hard to tell. It is a little better as far as heat that's available. This is going to replay that same test. Hard to tell the naked eye, and we're seeing it in real time. It's so quick. Hard to tell that there's really any difference between that and the first test with no fuses. Now we're going to go to the RK1 style. So like I said, 80% more current limiting than an RK5. That's pretty drastic. We can see that one with the naked eye on what we're doing just by jumping to that newer, latest, greatest fuse. And essentially it's switching from copper elements to silver elements. The film may change a little bit, but it is going to help reduce arc flash safety. And that's kind of high level overview.